To start, so in the previous class, we talked about the baseline, right? So, oh, you don't have anything on the screen. So we talked about the baseline, and we also basically defined a couple of things that, like, if you try to build a project, there are a series of questions before anything you need to ask, right? Like well, do I have the data? Do I have the, I don't know, like, do I believe this work? Do we have the labels for those? And, you know, series of questions, it's kind of like a scoping. You go through all of this. But one part of this was that it's definition of a baseline, right? And we also remember we talked about that human level performance, and like if you were going to work on a project, you ask basically two questions. If it's a structured type of data or it's unstructured data. If it was unstructured, like audio, text, I don't know, like an image, video, anything that's basically unstructured data, we use humans as like a human level performance as a really good baseline. We say that if humans, for example, perform 90%, you know, that's the target that we are basically hoping to reach, or maybe at some point basically surpass. But if it was a structured data, like a tabular data and stuff like that, we say that humans, we are really bad in reading and understanding tables, so we don't use humans as basically baseline or source of truth. Okay, so now we're going to talk about here, go over the concept of baseline and say that why the definition of baseline is difficult. Remember when we were talking about the labeling, what I said was that if you, for example, hire somebody to label your data and you're paying you know, it's a good amount of money out of pocket basically for someone to label your data. The last thing you want is that to hire somebody or a group of basically raters, and you don't have a proper labeling basically instruction. So everyone basically gives you a different answer basically, right? So example here is that, so if you think about this image, and this image basically, the labeling instruction says that use bounding boxes to indicate basically the position of iguanas. So that's the labeling instruction that you give to whoever basically you're paying to label for. And you get this from three different basically raters. Okay. Which one do you think is correct? One? All are correct, right? Because you have said that to basically use bounding boxes to indicate the position of iguanas, right? The one on the left position two iguanas. This one basically positioned one iguana and a larger one because it wanted to include the tail also. And this one basically put both in iguanas basically, right? So if you think about this, an image like that, you end up with three different labels, right? So this makes this really challenging for your model to learn technically. So the labeling instruction is pretty important from the perspective of from the perspective of your data. Now, again, this example we saw that same for the scratches on the phone, and you have the same idea. It says that use boxes to basically detect scratches. One person selects that as a scratch, ignores this one because they say, oh, that's not a scratch to me. The other person select those, and the other person basically select like that. And again, these are all correct because your labeling instruction is not clear enough. That's like what do I mean by a scratch? Okay, what's the definition of a scratch? Maybe you, for example, you could have said that use boxes to select basically or detect scratches that are longer than this size or this length width, for example, right? Then you could basically give the better basically instruction. Now, when we go to a concept of data, the first thing that we have is going to be defining basically baseline over your data, because it's pretty important for you to have a baseline to something that you want to compare against, especially if you're doing a labeling and you're doing a supervised task. So you want to be sure that you have the label because it's supervised, right? Now, let's look at another example, the example that we saw in the previous class for the audios. So you hear the three audios, basically one that says nearest gas station. The other one says nearest gas station. Just the amount of basically pause, basically it's longer. And the other one just says nearest gas station. And there is some sound at the end that you basically you're not able to detect. You're not able to transcribe, right? So here is the scenario is the same. So, there are label ambiguities here. You don't know basically which label is correct. Now, think about another example, like here an example of the structured data. And there's this user ID merge, for example, is a popular technique that we have in industry that when you have two different data sources and your goal is that somehow merge this together. Because if I'm able to merge this one with the other one, maybe I could do a recommendation, So here, imagine you have this website that's for job boards, and you have this basically person information. Okay. Then there's another website, or this one comes through an app for resumes, and you get this resume. Okay. Now your goal is that to understand if these two persons are the same, right? What do you think? Are they the same or not? We can't say, right? Just because the zip codes are the same and they have same name, that doesn't mean they are the same, right? It's especially if you live in a country that's like a really large population, then that becomes impossible, right? So that also becomes, so how could we basically match something like that? How could we connect these two together? Now, when we come to definition of your data, there are two questions that you always need to ask. Is like, okay, the first one was we ask a question like, do we have a data? Do we have a label for it or not, right? Then you look at the data and say that, hey, okay, what is the input that I have? What's the input and what's the output? Okay, so basically you have if this is assuming that you're doing supervised basically task. So you figure out your input, and then you're looking at the image and says that, for example, I'm doing image processing here. There's a lightning, contrast, resolution. Those could be the input, the features that I'm using. And you basically decide on what features you want to use. And this is sort of like part of your processing that you do. And when you go to the labels, the first question you always, and if anytime you get a project and says that we have a label, the first actually question you need to either ask or you figure out yourself is that, are the labels consistent? Okay, because again, it's highly possible you work with the data for a long time, you're assuming this data was good, and then you're always like, why the result that I'm getting is bad? And if you go back on the data, you will see that the labels are bad. I personally had experience like that. We paid to Amazon to do some sort of like name entity recognition. Is kind of like you give text document and says that find names, IDs, and stuff like that for us. We get lots of documents basically. We basically get a really large data set back, and we went over some of those. We were like, okay, the error is around like they themselves they were saying that error is between like a 5%. We were like, okay, it kind of makes sense. You do some sampling. Almost like 2 years later, I was still fixing labels. Like we have this model, like it's like this, one of the models, like why this error keeps coming up. And I'm like, I need to figure it out. I've just picked that one concept of one error and I went to back all the data that we have. And I've just tried to find wherever I see this term. And then I look at the labels, I was like, so bad. So on the grand scheme of large files, it was really bad. Amazon is not 5%, it was like a 20%, probably 30%, right? So that impacts you, especially if, if your labels are not consistent, then it just doesn't make sense. How much you try, doesn't matter how good is your model that you are trying, that error, that noise will be basically part of your model. Okay, so now, so we're going to talk about major types of data problems. Again, we do the same practice here in structured data, unstructured data. Okay, so let's start with unstructured data. So if you have unstructured data, you have two scenarios. You either have a small data or you have big data, it's a large amount of data. Okay. So, and then if you have a structured data, same small data, big data. Okay. If you have unstructured and a small amount of data, let's say this example of this phone inspection, and you have 100 training samples, because if you have a small amount of data, it's highly important for you to have clean labels. That means every label should be exact. So you have a really precise labeling, because you don't have enough data. You can't basically have a small amount of data and also have noise in your labelings. And same thing when it goes to structured data, like if you are doing a house price prediction, if you have a small amount of data, you want to be sure that you have a really good basically labels. But when it goes to big amount of data, large amount of data, there's certain level of noise that's basically your model should be able to handle. It's like, because it's large amount of data. With more data, basically, the practice is that your model basically will be able to basically distinguish the noise to some extent. But also that depends on how much is that noise. It's like a 5% noise, 10% noise, or 30% noise. That impacts also. So then in the big data, you put your emphasis on the data processing. So here you put the emphasis on the labeling, because I want to be sure my label is really good. But here I have lots of data. I would put the emphasis on data processing, like how you process data, how fast you can do that, how basically what are the steps that you are taking, right? So you put that basically process there, or emphasis there. Now, unstructured versus unstructured, again, in unstructured data, you might not have lots of basically labels. Humans can label the data for you. Data augmentation is pretty useful. And we will talk about data augmentation at some point in the class. But it's basically a practice of, like, if think about an image, if I have an image, I could basically do certain perturbation on that image that it doesn't change the nature of the image. That means if there is a dog in this image and I perturb this somehow, whenever you look at the perturbed version, it should still be a dog. If you change the data, perturb the data, and you look at the new data and say, I don't know what animal is this, then you cannot use that augmentation, because then your model also won't learn it. So that we will talk about this later. When you deal with structured data, normally it's more difficult to obtain more basically data, and human labelings are not basically that possible, or pretty basically rare. And again, now there's small data versus big data, and we say that in the small data, clean labels are critical. You can manually go through the data and basically try to fix the labels, or basically multiple engineers could go through the data and basically try to fix the labels. Your labelers, basically, they can talk to each other. So let's say I have 1,000 images and I want to label those, and I have hired, like these are like, let's say, medical images. So I have hired certain basically domain experts. And because it's a small amount of data, so those basically experts, domain experts, those maybe the radiologists, they are okay to basically interact with each other, to talk with each other. In big data, you just focus on the data processing. Normally, the practice of having your raters to interact with each other is not a really good practice, because you don't want them to bias each other's opinion, right? So that's why a small amount of data makes sense because, you don't have that much data, the bias might not be that strong, but if you have a large amount of data and you let everyone to talk with each other, that easily you will see the distribution of results shifts toward one's opinion, basically, who has a stronger opinion, right? So just be careful of those. All right, so let's look at this one. And again, the concept of label and consistency. So you have this is like a small data and noisy labels, and you're trying to just fit a linear regression basically line to it. And any of those lines basically could give a perfect basically result. Any of those lines that you see over here. If you have big data and noisy labels, that's the idea, is that the model anyway basically will find the way to go through the center, right? So it's like the noise doesn't impact much. If you have a small amount of data and clean labels, basically, that's a perfect scenario for you. So you just need to think about, especially for your project, if you have a small amount of data for your project, focus on be sure that your labels are really good. Like even if it means to manually, you and your teammates basically go over the labels that you have. And again, remember, if you even download the data from online, especially online, like someone has labeled that data. It's not like it came out of the nowhere with labels. Some humans has labeled it. So don't believe the data doesn't have bias or doesn't have, I don't know, like a inconsistency. So if something doesn't make sense, just go over it yourself. And normally it's good to do some statistical basically test around your labels and features and groups, for example. But that means that if you expect, for example, certain certain features, for example, or certain, let's think about the concept of like a house price prediction, right? So imagine you have this data set and this price of the houses, and then all of a sudden you look at the distribution of 1-bedroom house versus 2-bedroom and 3-bedroom and so on, and you feel like there is one of this 1-bedroom versus 2-bedroom, and one of those has a really strong shift in compared to the other ones, right? And you're like, I don't think something doesn't make sense. If you feel like something like that about your data, then trust your gut. You just go actually look at the data and be sure that those labels are real, or the labels are good, basically. Now, in example here, so we're trying to detect the scratches, right? So you pass this phone to how many people we have here? I have like 8 raters. So there are 8 different basically labelers or raters. And you have asked them to basically label 1 or 0, okay? So, and you get this answer. So basically, and again, this is not for the same image, there's different scratch lengths, basically. So you get, for example, these 3 that say they're not defective, and those 5 that say they are defective. But when you're looking at this, you basically say that this one has 0.3 millimeters scratch, was labeled as not defective. The other 2, they have almost like a 2 and 2.5 millimeters, and they were labeled as basically defective or scratched, right? So from the labeling perspective, that's not consistent, because if you think about a simple model that you're trying to just put a cutoff above 0.3 to be like defective, this model will fail, because you're like all of a sudden there are 2 data points before that. And maybe the good scenario for you is have something like that. And again, maybe this idea was for you to just say that at the beginning, say that, hey, we call a scratch to be like a defective if it's more than 0.3 millimeters. Right? So you define those basically rules. Not you shouldn't let them to decide based on how they feel about it. So. And it's also important to remember the big data problem also have some, long tails challenges. So when you have large data, normally you end up with some long tail on the data. The reason long tail is that they're rare events, right? You have lots of data about events, but then there's some events that are basically pretty rare, right? So that is normally challenging. So it's really important to keep those in mind, because again, not that they are not useful. You shouldn't think about like, oh, these are like outliers. They're not outliers. They're just rare in compared to this ones, right? So maybe you need to have a different system for those types of data, or give them different weightings, basically. And again, these are the three examples of the long tail. Could be web searches. If you think about web search, and Google has, there are certain searches that are pretty common every day, and there are some searches that are pretty rare, right? Self-driving cars, it's like there are certain patterns for self-driving cars, which are just common. And also, for example, how often would you see I don't know, like a cat on a bicycle, right? So it's like some stuff that don't make sense, but I don't know. And product recommendation system similar, there's some products pretty rare. Someone built something really rare, and maybe there was no other users to try to buy it often. So the recommendation engine maybe doesn't recommend something like that. It's kind of like in the long tail. So the next thing comes around improving the label consistency. There are a couple of practices that you can keep in mind. As first thing is that have multiple labelers to label the same data. That means don't just give everyone one data. You want majority votes on labeling, okay? Because easily you can basically get biased by opinions. When there is some disagreement, have maybe machine learning engineers or some SME subject matter expert to basically become the judge, to just make a final call or to review that. If your labelers, if you give an image to a labeler, for example, and you see that they are not sure about the labeling, they're like, it's not clear. Just trust it. Just remove it from your data. Don't just say that. Oh, just label it. Don't. That's wrong. Even if you are paid for the data. And iterate enough. Basically, you need. It's kind of like everything is like an iterative loop. You iterate basically until you get to the subset of your data that you can't do anything with this, and just drop this. So, I personally have a couple of points to add here. Have done years of labeling manually for myself. So what we did, one practice that we did in the company was if you try to have someone to label for you, basically you will have rules that you're only allowed to label 2 hours, in a row, because why? Because if you actually label, you understand it's pretty damn boring, and it's like a tedious task. It just needs to, since you read something and you're like make a decision. At first, you're like pumped up. It's at the beginning of the day. You're like doing good. As time goes, the labels decays, right? So you have rules that it basically for labelers like you're only allowed to basically label within this certain time period. Like normally you do it in the morning, and after, for example, 2 hours, they lose access to the server, because they normally get paid per hour, or per file, depending on what types of who you have hired. If it's like a domain expert, there's something really difficult, it's normally per file. If it's like general raters that you hire on Amazon, for example, those are per hour, right? I don't know, maybe they charge us per file. But so you basically will put thresholds on when you can do, how often you can do, and overall, how many files you can rate basically per day. Okay, because again, at the end, the person who's doing the labeling, they just want to make the money. It's not necessary that they want to give you the best result. Just keep those in mind. The other thing that also is important is one practice that I often do is that when I deal with labels and considering some statistical characteristics of the data and the labels that we have, I basically create 3 categories on my labels. Like if it's let's say I'm doing a binary classification, I have for class 0, class 1, and I have the middle class. So any file that, let's say you give a file to 10 labelers to label for you, and you do majority voting, right? So I put a threshold and say that if 70% they said class 1, I would basically say 1. If, for example, 70% they said like anything large value, they say that it's class 1, or the other class, I will select anything that less than like around 50, 60%. It's like a kind of like a maybe by one, like 5 out of 10, 6 said yes, 2, 4 said no. I don't use that data point basically, because it's kind of like it's not that sure because it's like even a model binary classification. You have a 60% versus 40%. You're not that sure actually because you draw the threshold, right? So those are some practices to just keep in mind. It's especially for any of you in the future that you build your own startup, and at the beginning of startup life, you need to pay for those labelings if you want to get data. Let's be sure that you first have everything set up before you go and hire raters. Okay, so now it's just 2 examples basically. How could we improve the add consistency to our labels? Is that so basically here you can standardize this 3 and you just call those like that. So you can maybe sit with the labelers and say that, hey, if you have an example like that, this is how you're going to label it, right? Or basically here, you have this definition was a deep scratch and shallow scratch. You're like, I don't want that. I just call it a scratch, right? Because it just adds more classes. Maybe it's not, because at the end, from your perspective, again, it depends what you are doing. If it's a scratch, you're just going to call it defective. Doesn't matter if it's a long scratch or short scratch. As long as it's defective, it's defective. Maybe your task is something different. Maybe I'm building a product that the goal is that to see long versus short, and then I want to figure out where they come from and why this one has long ones. Those are going to be different reasons, but normally try to have some sort of like a normalization on your labels. This again, another thing was here was that you could introduce maybe a 3rd category, and here you have defective or not. That's labeled. Maybe you could introduce different labels like a borderline, basically, like a something that I'm not sure defective or not. Why? Maybe you can pass that data to go to a different channel. That could be also another way to do that. And if you're dealing with audio and if it's unintelligible, if it's something you cannot detect, just label it like that. Instead of trying to actually instead of trying to figure out what was said, what was the word, just put something like unintelligible, right? If you actually look at the YouTube, like if you watch any video with subscript, like transcript, you see that happens a lot. Right, you will see that, especially if you watch for our class. It's like most of the time when I talk, it actually says unintelligible. it doesn't detect. I have seen it myself. So it's good because it doesn't try to figure out what was told. If the confidence is low, just say I don't know, right? So okay, this just for unstructured data. When again a small data you normally need a small amount of labelers. Again, they can talk with each other. Big data that you have, first get a definition, first try out some sort of a trial with a small group of raters and see if they basically understood the guidelines that you gave them, if the result that you got basically is good. Actually, we did also do a practice like that. So at some point, me and my team, we need to label ourselves. This was the first time we were 4 years ago, we needed to manually label. So the best thing that we did was we first send a document to everyone and say that, hey, label this. We just wanted to know they work in the company, but we wanted to know that what do they believe is the definition of, for example, a threat in cybersecurity. And we just got all over the place results. Even same engineers that were building it, because it's the definition wasn't clear. So then we went through the practice again. So this time we added some, just more instruction. This is what we do. So actually, I hold a meeting, and I was in the meeting. I went over example. I said that the reason this should be this is this. So I tried to give them the guideline, and then we repeated the experiment with the new data. This time we got about an 85% agreement, but we wanted higher because it should be higher. We went another round. We basically raised that to about 93% basically of label, which is actually 92 to 93% is human level performance for labeling a file as a medical file as a sensitive or not sensitive. That means if you open medical documents, you put it in front of someone and say, hey, do you see anything sensitive in it, right? and they basically say yes or no. Humans are about 93% accurate. Because there's some definition about document and the sensitivity levels. So, so that's again, that's what we did. We did with a smaller group, then we basically expanded. Yeah, that covers everything that we just talked about. Okay, now let's go back to human level performance. All right. So, and this comes back to what I was just talking about. When you, for your project, you get a data. Well, the first question that you ask, well, who has labeled this data, right? So some other human, right? So now think about here. So you have this data set, and this is the ground truths, the labels, actual labels. And you are basically testing it out, right? So you pass the data, not the labels, the data to some inspectors, some people that you're hiring, for example, and say that, hey, what do you think about this phone? Like the scratch in this example. And you get these results. Scratch, not a scratch, right? So when you compare these two together, and you see I have 66% accuracy, like they agree with each other, then that should be pretty questionable. Why? Because your first thing is that, oh, I'm hiring an inspector, they're a domain expert, right? Why they're only 66% basically accurate, right? So, but the other question that you also need to ask is that, who did label this for us? Right? This was another human. Are they actually accurate? So it shouldn't be, you should basically look at the problem both ways. One is from the perspective of the labelers that you have. The other one is from the perspective of the data practice that you have. This is the part of the practice that you want to do. Your goal is that to be sure that these are matching, 99%, 100% matching. There shouldn't be a reason that they don't match, right? So now, in I think we talked about this in the first class, but and one of your friends also here would say that the academy, that's what we do always, right? It's like every paper that comes to the market, every model that comes to the, basically what we do. We basically, you have the same data and everyone's trying to beat each other with a different model, right? So that's basically what happens in academy, right? But when you go to industry, that's not the case. First thing is that your goal is not to just beat someone else's model, because first you don't have access to their model, you don't know their scores, stuff like that, right? Your goal should be that I want a model that works pretty good, right? It's a consistent within the framework that I define. Now, you might be asked this question as an engineer when you do working that, again, I have been asked this question so many times. We talk about building a model like a 199% accuracy. That's like a really common, basically, request, right? And the first question is, well, is that reasonable? Can humans basically do the same thing, assuming that this is an unstructured task, right? And there is another thing also, is that this view of like outperforming human level performance. Like we're going to build a model that outperforms humans. We're going to basically do that, right? That's just like this view of like, not that it's not achievable, because as we have seen certain basically tasks, for example, if you think about basically in generative AI, basically the whole idea of building, like if you ask ChatGPT certain questions, for example, for labelings, it's outperforms humans, right? Or basically if you think about the concept of like word understanding, like a word from, or basically transcribing, right? Now the model is basically doing it better than humans. You need to add lots of basically layers, much larger models, right? More expensive. But it's possible basically to do better than humans, but that shouldn't be the goal. That shouldn't be, I want to build a product that's, you know, just going to outperform basically humans, right? But why not? Why we should be cautious about that? So think about this example. So you have two text. You're passing basically, you have this audio, you pass to your raters, different group of raters. And you get the result, like they give you the transcript. You get the first one 70% of the time, and you get the second line 30% of the time. Okay, so let's say you have, I don't know, like you have 10 basically labelers, 7 of those given that, or basically 3 of those given that. Okay, so if you think about from a probability perspective, the chance that two labels agree with each other, considering that 70 and 30 is 58%. Okay. So if you randomly picked out of those labels that you have two, the chance that they agree with each other is 58%. Now, what do you think ML model will give you as an answer if you give that data? Majority, always majority. Machine learning models, like it's kind of like if you put 100 of yes and 20 no, the model basically learns to go with majority vote, right? So your model basically says 70%. So did I outperform humans? See, from the perspective here, you actually outperform human level performance. But did your model actually learn or just give you the majority answer? So that's why I say you need to be really cautious when it's like the goal is to outperform humans, you know, you need to be really cautious about that. Like what does that mean? Okay, because you can easily think that you have done that, but you know, you haven't done. So now raising HLP or raising human level performance, it also comes back to example that I was talking about. That we did the practice and we're like, the result is not good. We did some training and basically tried to raise that. Now, in this example that we saw, for example, we go and we do a test study over the actual labels that we have, and we find that this one was supposed to be 0, right? Like it was a wrong label, basically. And you go over, talk with the inspector, and you define a rule and says that, hey, if the scratch is more than 0.3, call it a scratch. If it's less than 0.3, don't call it a scratch. And this one from 1 will change to 0. Now you have 100% basically match, right? And basically what we do as a study here was that we just look at both scenarios to see why they are basically disagreeing with each other. And your goal again for your project is that when you have wherever you get that data, look at that data, be sure that you have consistency on your labels. If it's a smaller amount of data that you can manually go over, do some study, improve the labels, definitely do that. If you have a larger amount of data, so have some idea of what assumptions that you are taking or what's the process that you're going to go through. So this comes back to the same thing we talked about. Now, human level performance on the structured data, again, just to summarize, we already said that humans, we are doing really bad at this task. The reason is that if you think about the user ID image, you know, it's like you ask a human, like, I don't know if they're the same people or not. Or based on network traffic, is this computer being hacked? How should I know? Right? It's kind of like impossible for us to say something like that. Is this transaction fraudulent? I mean, I don't know. I don't know your history of transactions. Even if I know, I cannot analyze it to see that if it's possible. A spam account, you know, it's like pretty hard for us to decide if someone is spamming. You need to be really clever about the emails that you receive to decide if it's a spam or not. And from GPS, for example, could you say if this person is on foot, on bike, on car? Yes, of course we cannot, right? So those are the type of reasons that when it comes to structured types of data, humans, we're not doing a good job, right? And that also itself makes it challenging because where should we get the labels for this, right? So there are lots of companies out there, probably you know that they sell data, right? They just basically create this synthetic data, tabular data. I did at some point wanted to buy data for some model that we were working on. Went over with series of these companies, I'm not naming any, but their data are pretty bad. There are some good data out there. It's like but when you look at the large amount of data that you are trying to buy, so you don't know where this label's coming from. You know, it's a kind of pretty synthetic, like graph, maybe a structure. They have put anything that's similar has same labels, anything that dissimilar has different labels. So it's really difficult to get this type of data. Now, the next thing comes around the obtaining data. Okay, so it's a good practice here. When you want to work on a project, it's like At first, basically, we're going to understand one thing here. Don't ask this question, how much data do I need to build that, right? Like, when I can get this much data. That shouldn't be your motto. Your motto should be that if I want within the next 3 days to start, how much data I can acquire in these 3 days, right? Like how much data in a small amount of time you can basically acquire. Because the whole idea is that the sooner you iterate, the sooner you learn, basically, the faster also you process. If you basically, it's like the idea of like a perfection is the enemy of completion right here. So just pick maybe assign only 2-3 days to finding data, get some data, process through it, do something, learn something, get new data and continue. Don't try at first to have all the data and everything, right? And again, remember, as we talked about for your project, is that the goal also for you is that to be sure that every piece, it's basically works. If I remove this piece later and replace it with something else, the whole pipeline will work, right? So that only works if you have some idea like this, rather than to make it perfect. Just build something and iterate over it, okay? So let's go here. Now, inventory for data, so it's just the numbers are not, the costs are not accurate. It's just basically assumption. But the way that you basically can source data right now, you could own the data. It's own data basically means that you have done a study yourself. You collected data, for example. That's owning data. Crowdsourcing basically the data. You can basically crowdsource from the Google. Like you basically scrap the internet. You can pay for the labels. That's a scenario. There are lots of unlabeled data out there, and then you basically can get those, and you can pay to label those, or you can basically purchase find a company that's selling the data. So these are basically the 4 options that you can have for acquiring data. Now, you basically need to have some idea of like how much it will cost, how much I have, how much it will cost, and total, what's my budget. Basically, you can get some sense of which direction is better for me to go with. So now when it comes to the labeling, the first basically option here is that the question is that should we do it ourselves or should we basically in-house versus basically outsource? So just make it 2 separate, then we're going to break the other one. So in-house versus basically outhouse. And I told you I have done lots of in-house labeling. The one thing we learned is that if you think about your engineer's perspective, how much you pay for their salaries and stuff like that, you shouldn't have your engineers basically to label, because you pay way more for the wage than to basically have them label data. It might be good because they basically maybe do a better job in labeling, but it's not going to be a financial, basically a good financial decision. So one thing you could do is that maybe it's good for your engineers to do a small amount to learn the difficulties of the data, some challenges on the data, but not necessary to be the source of labor. So that's the idea of in-house. Then you can outsource versus crowdsource. So outsource basically, again, you have data that's on the internet, you have labels basically outsource that labels, or you pay somebody basically to label it for you. Those become outsourced. Then crowdsource means that one idea of crowdsource is like if you think about this like let's say I want to label one document and I pass it to ChatGPT and I pass it to Gemini as crowdsourcing. So basically you have different models to do the labeling and basically you basically combine those. Now the crowdsource could be you could actually write models basically that like some sort of like ensemble models basically, for example, something like a weak classifiers, like there's this idea of like a weak supervision that I built series of smaller labelers and basically I let them to run over the data and I aggregate those. Okay, we have a lab on that will come up. The really good, there's a good library by Stanford NLP, for example, for it's called got the name now. Anyone here? Stanford NLP? I forgot the name. Anyway, so it's a pretty good pipeline for basically writing your own basic ensemble labelers. Now, who's qualified to label? You need to be sure also you have some understanding when you want to basically have the labels, like depending on the tasks. If it's a speech recognition, maybe anyone who can fluently speak English, it's basically qualified. If it's a factory inspection, medical image diagnosis, stuff like that, now you need subject matter expert. It cannot be anyone, right? If it's a recommendation system, basically, it's probably going to be impossible by humans to label it, so it doesn't matter who you have. The last thing here is that don't increase data by more than 10 times at a time. That means, again, iteratively, label for a certain amount of time, continue with that new data that you have, and then label again. Just don't try at first to label all of it or pay for all of it. Now, the next thing comes around basically the data pipeline. So think about this example that you have. So you have two sources of data that's coming through. You have a website and you have an app, okay? And raw data basically here, this is your data pipeline. So raw data does some cleaning, and first you get rid of the spams, basically. You try to merge those two user ID merge, and then you pass that data to your ML model, right? So that basically, this process becomes your data pipeline. So from the raw data comes the process that goes through, processing it, having it ready for your machine learning model to basically digest that. Now, when you think about the data pipeline, you need to always remember that you normally start as development, right? So that's your development when either you or your data science team basically, they get data, they do all these processing steps, they have a clean data, they build a model over that, they do set up test performance, right? But one thing that's really important is that in production and when we deploy, you need to be sure that this pre-processing is replica, it's identical. A small change in the data pre-processing pipeline, could easily change the nature of the data for your model. And your model result could end up being different, okay? So it's really important to be sure that whatever data pre-processing you build as part of your development should be part of your deployment. That means whenever a user comes, the data should go through the same pre-processing steps, right? We will go over the practices on that how to ensure that, for example, as one simple idea here is that if you think about when I centralize my data, so let's say I have a data and as part of the pre-processing, I centralize the data. How do you do that? I find the mean and the standard deviation, right? Centralized. And I do that over my training data, for example. This is just imagine you do training. If I want to, as part of my deployment, user comes to enter the data, I need to be sure that I normalize or centralize that data using the same mean and the standard deviation from the train data, not the mean and the standard deviation from the customer data. Why? Because if you think about it, when you normalize or centralize, you shift the data to have a center mean 0, right? And the standard deviation, for example, 1. But you basically shift the data to a certain, basically, over the scale. Now, as part of inference, maybe that distribution is here because they end up having a different mean, basically. Right? So you need to ensure that whatever statistic you use during the training for pre-processing to carry that as part of your deployment pipeline, pre-processing for inference, basically. Okay, so again, we will go more in details, but you need to be sure that this is replicable. Then it comes a concept of POC and production phase. So POC, again, proof of concept. Your goal is always, as part of POC, is that decide if this idea that we have is worth pursuing, basically, is something that we can put it in the product and we should do it, right? So normally as part of POC, you just build something that works. The goal is that maybe in the fastest way possible, your code doesn't need to be clean. Build something that you can test it, okay? I build a prototype that can work. Then I test it. If At POC, again, we said that the idea was that maybe you have some early adapters that they agree to let you run your model on the data or on the environment, or maybe you promise some discounts and stuff like that. Those are just all policies, but that's the POC, right? So you run it. If the result of the POC was that, yes, this is a good model or this is a good product, customer is happy, it does what we expect, then you go to production phase. Now you basically spend the time on making the code cleans, do all the testing, proper testing, as basically be sure that this is now well-written, basically, product. So as part of POC, normally the goal is that have something quickly done that we can test out. Because, again, you don't know if it's going to work, the idea, or not, If it's there's some differences here that sometimes, for example, you might have done already some research and is like you have some sort of like a proof of concept done. And you're like, I already know it's worked. We know we have proved it, we published it and stuff like that. We're just going to build it. That could be possible. But most of the time in companies, it's not like that. It's like you want to build something, so you do it super quick, test it out, and if yes, then we continue with the actual product or production phase, basically. Any question on those? Now, so this list of that you see here, we have all of those basically as part of the labs that we will see later. Now, the next thing when it comes around this data and labels and stuff like it comes around the metadata, data provenance, and lineage. Okay, so let's just start with the provenance and lineage. So think about these. When data comes, someone's data comes to your network, or basically data comes to your company, enters for the first time to your network. From the moment that data comes to your basically network, you as a company are responsible for that data, right? So now think about, I have this data scientist that basically they download data from the database that we have, and they do all sort of processing. What happens here is that at certain point, you have all sort of derivations of this data across all the machines that you don't know where are they. Or how often you worked on a project for yourself and you built so many copies of the same data, save it on your machine, right? I have done that a lot, right? So it gets to the point that you basically lose the track of, it's like that data. So that's where basically the term provenance and lineage comes from. So provenance basically focuses on like where this data come from. So where this data come from, where it is, right? Lineage, it's the focus on the sequence of like a processing that this data is going through. This data come to my machine, to my network, went through all this process. So that's the lineage of the data. You as a company, you want to have a track of lineage and provenance, right? So now in the, depending on especially where we are geographically, it's actually the rules are a bit different. So if you are in Europe, there's a basically GDPR, governance data protection rule, where every company is responsible for any data that comes to the company, basically from the start through the end. And you as a customer could easily basically write a letter and says that remove my data. And they have, I think it's like a week or 10 days time to prove and send you a letter back that we have eliminated all of your data basically, right? So European companies now, because this is enforced, they need to have lineage and provenance, okay? US is not the case, right? First, I think right now we only have California, state of California. They put similar rules like years back. How often have you tried to apply for a job and on LinkedIn or a company job, on bottom it asks you that if you are from a state of California, that's the reason. They need to treat your data differently. Right? If you're from California, there are certain rules applies. They need to keep track of your data. So if you write a letter in California, if you're from the state of California, if you write a letter, they need to remove your data. Okay. I have personally wrote letters to certain companies so many times that to remove my data. I never got any answer back. It's like, doesn't go through. I even actually found something. So the one thing about it is like the removing your data. The other one is also that if there is something misinformation about your data, they are supposed to fix it. If you search about my name on Google, it comes and says that my university, Vienna University. And I'm like, I never been to Vienna, I never studied there. So I wrote to the Google basically team like 3 times, emailed them, and they asked me for all sort of proof that this is me. I was like, I provide all sort of proofs. They never fix it. Then after that, they never respond. So it's like that, you know. In reality, it's like that. In US, like it's like you don't have much control over your data. In reality, you can fight it, but normally those companies they have a better lawyer than you, right? So I think the plans are as we move forward, states are putting new rules and the new regulations. I think New York did some, Massachusetts is doing something, but it's going to be really challenging. Now, think about this one. So you have this pipeline from here all the way through here that you make a prediction. So this is like the total pipeline. And how does this pipeline work? So you have this data set, a spam data set means the data set that has bad data also. And you have this ML model that goes over that data and de-spam, basically anti-spam. Just gives you a cleaner version of that data. So this is the output basically. And so you have a spam data set, you build a model, you bring user data, de-spam it using the model, and you get the de-spam, right? So now that's a de-spam data. This has come back from the same table that we saw, job search and resume. And then you have this ID merge table. You have an ML model, you build a model over that. And you basically apply this there and you get a clean user data. So a user that's kind of like has ID merge basically. Then you build another model over that job search model and you make a prediction, for example. So this is like the whole pipeline. When we talk about provenance, your basic goal is to know where are this data coming from. But when you talk about lineage, these are the lineage of the data. You need to be able to answer back where this data goes by, but not only for laws. It's not just for the user perspective, for your model or for your basically analysis perspective. Think about this. You have a pipeline like this. It's pretty complicated, right? If you don't have a proper understanding of the lineage of your data, if something goes wrong here, how do you know who's responsible, right? But if you have lineage, you can trace back. Okay, this data, let me see what happened here. Let me see what happened here. Let me see what happened here. You go through a lineage, basically you try to understand. Or you have a proper logging already, for those lineages. And when some error comes, you just look at the logs and say, oh, the error comes from this part. If you don't have a lineage, you're pretty blind to that. Something happens, you just need to do manual debugging. Okay. Is that clear for everyone? All right. Now, when it comes around metadata, you also think about when you have a product. Remember we talked about your product is not just your machine learning model. It's everything around, right? So for example, if you're in a factory that, again, the same example that we have been going over, there's like images of the phone, or scratches. Now, there are certain basically data that you collect, which come from the phone itself, but there's certain data, metadata comes from everything around. For example, what was the time? What's the factory? What's the line number? Basically information around the camera that takes in that photo for you. What's the phone model? Well, so on. If it's a speech recognition, remember we talked about that it's not only your model, it could be actually the VAD, like a voice activation detection module, the different software or piece of basically hardware that basically get the data for your model. So if something goes wrong there, your model also going to perform bad. So metadata means that don't only collect data from your model, collect enough data for things around it. So if all of a sudden you get an error that this factory has lots of bad cell phone coming out. You don't need to manually go figure out what's going on. You go look at the factory's data, metadata, try to see all of a sudden what has changed. And maybe you find, oh, this line, for example, the lighting on top, this lighting, the degree of brightness all of a sudden decreased, right? So you can do those if you collect the metadata. So always remember, and I personally, me and my team, we do is that we collect metadata a lot at the beginning, and then we basically tailor it down, whenever we figure out which ones are not that useful. It's similar to logging. Log a lot at first, and then slowly you can get rid of them because you will figure out which logs are more useful. And the next thing comes around your balance. I'm sure all of you have dealt with problem like this, like especially lots of time data is like this, you just have a data that's kind of like imbalance. And again, we're not going to go over that, but you just want to be sure that whenever you have an imbalanced data, if you do a split, be sure that you keep the ratios the same. It's like a stratify basically sampling, right? So that means if you have 20% class 1 and you split your data into 3 train validation tests, every one of those also should have 20% with respect to their own size of class 1. Okay, so don't basically disrupt the population, basically. However, for your training data, you could apply different techniques like data augmentation, for example. If you apply, it will change the imbalancing problem because, it's just now you create more labels, basically. Or you basically apply smooth or whatever you apply basically, but you normally apply that to training data, not validation, not testing. You want to be sure the validation and test are the real data. Training data is you do some basically techniques to fix the imbalance, but just for your model to learn. But you also want your model to learn that that's just for during the training. That's why you ensure that your validation, it has same original basically ratio. Now, let's go. Oh, we already went over this. Yeah, okay. So all right, let's do this. It's a really interesting video. I'm going to play that. Before I play this, so I highly recommend you read the whole article. It's basically some practices that Google has put out there, and what they say is basically accurate. They are such a large company. They have done lots of try and error, so they have learned the lesson. So yeah, it's good for you basically to give it a go. So the video only talks about 9 rules, but I think the overall it is 43 rules. Okay, so let's do that first. Right. I highly recommend to read that article. It's pretty good. You learn something from it. All right. So what we're going to do, in order to, because we want to finalize the scoping. So the last thing we're going to now talk about, we're going to go over for like some time, and I give you a break like after like 15, 20 minutes. Now we're going to talk about errors and graceful failure. So remember, we said that's part of your scoping. It's a good practice to think ahead of time. What could go wrong? You know, what could be the error? You know, and what's the meaning of that? So to have those definitions, especially when you want to send out a product, you want that the user understand how to work with it and what's the meaning of it, right? So it's like, what's the meaning of the prediction that you make? Now, so the first thing we're going to go with three concepts: define errors and failure, identifying error sources, and providing a path forward if the error happens. So first, when we're going to over the defining the error and failure, I said at the beginning of the class, so in AI system, there are basically in software we have two errors, like a user error and system error, right? And again, user error is the scenario where, like if you think about like you have a platform and user does something wrong that you're not supposed to do. Like when they try to enter a name, enter numbers, for example. This is kind of like a user error. And system error basically is like on the other end when system is doing something wrong. Basically, system is not basically, you know, system crashing is not a system error, right? In AI models or ML models, we have a third basically error, and that's called context error. And that's not a part of the software basically. It's like in AI models basically. Now, in idea, the simple definition of context error is that AI models maybe give you some result based on some assumption that given the context is considered as an error, basically. You know? Now, think about a scenario like you have this example from this same booklet, but you're doing a recommendation system and you offer this user like a book, certain books. And every time you offer, a user rejects it, right? If you app keep doing the same thing, you know, that becomes an error, right? But that's an error because your AI basically need to learn, like a user is rejecting, they don't like this, right? From your AI perspective, it's AI is doing what has learned or trained on, right? But given the context that the user doesn't like that, that's, you know, becomes a context error, right? So it's going to be different. So you need to have some sort of learning, for example, over there. Now, when we come to this, let's look at this example. So remember we talked about this, this is the same booklet that we went over in the previous class, that you're building an app for run suggestion. You want to be a runner and you're building this app that if you open the app, it suggests you pass to run, it suggests you types of, I don't know, like, or maybe group that to go run with and stuff like that. Let's say as part of your app, you have a page for music, okay? And on the left, basically, here we see the user basically is about to start running, and your app basically gives you this option that ready to run, not now, okay? And the other one on the right, basically, the app automatically detects user running and it starts the run. Okay, so on the right, it's a wrong decision. Why? Because your AI makes an assumption that user was running. Right, so you see that becomes like a context error. Because however, on the left, basically, you let the user decide if I'm running or not. What's the context? Maybe I'm warming up. I don't want to count that toward my running, right? So your AI model shouldn't make that assumption. Now, when it comes to this context error and basic context error and user perceived errors, there are different types of error that we could deal with. So normally when we say context error, these are actually true positive. So context error, the term context error, that means your model is actually correctly giving the answer, right? Because the way that it was trained, if you think about the model perspective, your model is actually doing a correct job. But maybe given the context that, you know, that's not, or user doesn't receive it as basically the correct answer. An example is that if you open in Spotify. So I personally always see that. Like I never listen to jazz, never have listened. Spotify once in a while recommends me a jazz music, right? So I personally, from the perspective of like I never listened to jazz, I never played after you recommended. You know, it's like why your algorithm doesn't learn that, right? But from the algorithm perspective, maybe the algorithm wants to promote new, basically, ideas, new musics, new genres, stuff like that, right? So algorithm is doing what it's supposed to do, but from my end is like, okay, you know, it's an error, right? So that the context error means that it's not technically an error. The algorithm does what it was supposed to do, but it's seen as an error. The next one is fail state. Fail state is a scenario when the algorithm can't give an answer. Okay, so it's like you ask a question or giving a data, algorithm doesn't have an answer for you, right? And that's basically that doesn't consider to also be an error. That's also a true negative. You know, that means that when the model doesn't give you an answer, it doesn't provide an answer because certain scenarios, like a model doesn't have an answer for that. Like you ask if it's a dog or not, your model says no, and you keep saying it's dog. You know, the model keeps saying no, for example, you think it's like a failed state, or the model doesn't have answer. You ask ChatGPT a question, it doesn't give you the answer. Like you say, I cannot answer you that, right? So from your end is like this model. From model perspective, you know, that's a correct true negative. All right, that's called fail state. So. And this could be another example for you. So it's like a user on your app, you also have this section for music. And user goes over there and then they haven't added any music before. And then this page, this comes up, this like a error, not error, it's like a pop-up so come up, says that, do you want to add songs? Not now, find songs, for example. And on the right, basically, you put an error in front of user's face, like a no playlist long, not now, find songs, right? Kind of like that. So the idea here is that which one of these two is better. It's kind of like this one is better. You know, it's kind of like the way that user will perceive that same answer maybe. And on one becomes an error. He's like, oh, this is bad. On the other one, it becomes like, okay, you know, it's like, makes sense. Yes, I will find that new songs, right? And also, technically, you could maybe promote your other model and find songs connects to your other algorithm that does the recommendation and stuff like that. So it's like maybe it becomes a hierarchical basically model here. Now, then when it comes also basically errors, you know, errors that could be some sort of errors that we cannot perceive. That means errors that are kind of hidden, right? One example here is called happy accident as part of the errors is that like someone asks us, I don't know, like Alexa, put out the trash, right? So it's like kind of like they make a funny joke, right? So from the perspective, it's just called a happy accident. But you also want to be sure as an engineer that you collect those happy accidents, you know, because from the perspective, your Alexa didn't have an answer, maybe become an error toward what you're collecting, right? It might impact your future learning. So you want to be sure you collect those information. Or background errors. The background error in a scenario is that your model is not working correctly, your AI is not working correctly, your product, but user doesn't detect it. User don't know basically that if it's not working. So they don't create any ticket, they don't have any complaints, right? So that's also possible. You want to be sure these types of errors, these hidden errors are not basically going unseen by you or your team. You want to be sure you have proper logging that you can at some point detect this basically, okay? Because they will impact your solution. The next thing is that you need to always account for basically timing in the user journey. So we're not going to talk about this a lot, but if you think about whenever you want to build a product, there's a concept called user journey overall, right? You basically, let's say I want to build a dashboard. And one of the practices that you do, like a UX or UI designers basically, is what's the user journey from the moment that user comes to your website or to your app, what process they will go through until they're done. That you need to basically do all of those practices. It shouldn't be just building something, right? So you should follow the user journey to be sure that this process that the user goes through is actually like makes sense, it's not tiresome. Because now it's possible you build an app and you put it on the website and you see lots of downloads, for example. So lots of time people downloading the app. They're like, wow, it's going to be great. But then you get 10% only registration. 90% don't register. Then the question will be that what went wrong, right? So if you have done a proper user journey, you might understand that as user goes through registration, because it was so long or annoying, they stop. I have done that before, like try to register for a certain hour. I was like, no, I'm done. I'm going to download something else. They ask too many questions. It's so long. So that could be basically like a sign that, hey, you need to improve your user journey. Here, what we're going to talk about is that when you think about user journey, also think about who you're targeting. The users that you are basically having, are they someone new? Someone's the first time basically, or someone that they have had exposure to. So that's also basically going to have a different basically different behavior, different expectations. The other one is that you need to be sure that you give different weighting to situations, you know, or basically to the errors. So when you think about errors, your errors could have a low basically like a risk, or it could have high risk. If it's low risk, for example, low risk, we say the scenario that users has expertise. Right? Think about ChatGPT. You're all using it, right? I personally use it, right? So when you use it, again, for someone like us that we're using, like you're in the school or basically academy, that if I ask a question and I just want to answer, it's a low risk. Why? Because I will read the answer. If it's error, I will detect it, right? Versus someone, let's say someone that they don't have any knowledge and they want a quick answer and they ask ChatGPT and they believe it's so quick. That becomes high risk, all right? So you see that this weighing of these situations are really different depending on who's the users that you have. Then if your model has extremely high system confidence or many possible success outcomes, so just consider like a lower risk. When it comes to higher risk, basically, when you have something like a multitasking, basically, when you model has low basically system confidence, or again, when the user is totally new to the task, those are, you know, you give it a basically higher task. And you need to define those for your product as part of definitions. Then again, this kind of bit also, if you want to look at the situation, like a category perspective, lower risk, or if it's something experimental for play, for creativities, lightweight entertainment, non-essential recommendation, that lower risk. Like if you're on I don't know, Netflix and you get a bad recommendation, there's no risk in it, right? Versus higher risk is like anything that's around health, safety, financial decision, sensitive social context, or anything like for example, cybersecurity. Cybersecurity and everything that we do is high risk because you need to be sure that you don't miss something, right? So the situations are going to be different. All right, so that's summary over here. The next thing is that identifying the error sources. So you want to be sure that whenever you have error, you can identify the source. The first thing is that error could simply comes from your label data. And I say that that's highly possible. You find errors are like, it doesn't make sense. And when you go to your label data, you see that, oh, it was bad label, right? So it could be from the training data. It could be from your model. That means your model is just not strong enough, basically. So you need to have a better model, maybe. It could be from missing or incomplete data. That means the data that comes to your model had something missing or somehow incomplete, right? That could be the, again, the source of the data. You could have error that comes from the input. Like input could be like you have some unexpected input. User enters something that you didn't expect, like an unexpected input, for example. Could be breaking habitations. Like you all of a sudden change something about your platform, and user now you see lots of error or basically problems because user broke the mental models, right? So it's kind of like that could be also the case. So you need to basically account for all of this when you build an ML product. It's not again just your ML model. It's like an end-to-end product. Okay? So the last thing I should just talk about quickly is the disambiguate system hierarchy errors. especially, for example, the first thing is like multiple system. As you remember the example we saw that you had all these pipelines that you were passing the data, different models. So that becomes a hierarchical. So, error from first one could have compounding effect all the way to the end, right? So you need to be sure that you understand those ones. When it comes to signal, for example, what happens if all of a sudden signal crashes? Then what will happen? Like, will your model work in the background and later send the data? Or it's like what does it happen? You need to also account for those ones. All right. And then again, the last thing is just provide the pass forward from the failure. Maybe get user feedbacks. Always be sure that, have something like maybe thumbs up, thumbs down, or just to give me a feedback and use in reality, that thumbs up, thumbs down is perfect scenario for a company to get labels, right? Because you make a prediction, you don't know if it's correct or not. User tells you if it's correct or not, right? There's certain error rates, some error basically because of user that will be introduced. But if actually user gives you feedback, that's like the best label that you could have, right? And actually most of the time it's not the case. It's like getting feedback is not that common. All right. So let's just stop here. Let's take a break, and then we continue with labs after this.